all. So we're going to talk today about integrating with trigonometry and specifically talking about some of the advanced things such as here where you see powers. Now this is one of the cases where it's a lot of very similar problems that you want to attack slightly differently. So if I did every single problem in the guided notes, this would be a 25-minute video, and I don't want to do that to either of us. So I'm going to walk through a couple examples, and some I will encourage you to look at the attached PDF on Google Classroom so that you can see every single step. I'm going to leave some of them out. You don't need to watch me do U substitution 4 times. However, I will go through the first one completely, and I'll go through most of the rest. Now, what we're going to do, so let's get ourselves ready for notes, is we're going to talk about powers when it comes to trigonometry integrals, and we're going to break them up into categories. We're first going to talk about sine and cosine. So what we see here, cosine to the third, sine to the fifth, x cosine squared. And these are really straightforward when you have odd powers. So here we have 3, great, fifth, great. And if you have odd powers of sine and cosine, you're just going to use U substitution. So in this case, what I'm going to do is I'm going to take my odd power and I'm going to factor out one of the terms. And this is going to be the same steps that you do whenever you run into this type of problem. And the reason that we want to do this is so we can use U substitution. What you're going to do is, in order to use U substitution, this would have to be sine. So then du would be cosine here. Well, thankfully, we have a function that replaces cosine squared with sine. So you'll do your Pythagorean identity substitution. And again, like I said, this is going to be the same steps that you do for all these odd sine and cosine problems. And then you'll say, oh, well, u is equal to sine of x. Du, therefore, is equal to cosine of x dx. And you get a lovely, straightforward polynomial, which is 1 minus u squared du. If you want to integrate that, that would be u minus 1/3 u cubed plus c. And our final substituting back in, sine of x minus 1/3 sine cubed x plus c. So this method using U substitution and powers is going to be how you attack all these different problems. Same thing here. I'm not going to go all the way through number 2, but it's going to be the same idea. We factor out one of our sines, so we end up with sine to the 4th x cosine squared x times sine x dx. Whoop, cosine squared. Since we have this is going to be our du, so that means that we need to write everything in terms of cosine. This one's already fine. And then our integral will be sine to the 4th, so that's sine squared squared. So our integral would be 1 minus cosine squared x squared cosine squared x times sine x dx. So if our u is cosine, our du is negative sine, and we end up, as I've said before, with the very nice polynomial, the integral of 1 minus u squared squared times u squared du. I will let you integrate that polynomial and check your answers on the PDF. So when it comes to even powers of sine and cosine, you are going to replace using the double angle theorem for cosine. So in this case, what that's going to be is here we have cosine squared. So I'm going to use this formula here. I'm only interested in cosine squared, so I'm going to rewrite that side here as cosine squared, that's what I want, minus 1 minus cosine squared as a replacement for sine squared. Because remember, that's all I'm interested in here. So I can simplify that to say that's cosine squared x minus 1 plus cosine squared x which would be 2 cosine squared x minus 1 is equal to cosine of 2x. So the replacement that you end up doing is 1/2 times cosine of 2x plus 1 is equal to cosine squared. You could also do a similar substitution, which is 1/2 times 1 minus cosine of 2x is equal to sine squared. So these are going to be the two substitutions that are going to be the most helpful for things like number 3, because what that does is reduce the power. So here, I'm going to use that first one to say 1/2 cosine of 2x plus 1 dx. It's not a u substitution. X is the same all the way through. You don't need to worry about that. Factor out the 1/2, the integral of cosine of 2x plus 1 dx is now a nice straightforward. You can use the chain rule slightly if you'd like to. You can use a little u substitution for the cosine of 2x, but we end up with 1/2 times 1/2 sine of 2x plus x for the polynomial term plus c, and final answer 1/4 sine of 2x plus 1/2 x plus c. So these are two formula that are going to be really helpful to have just written down as you're working through this homework. So as we have sine and cosine together, you might also have tangent and secant together, or cotangent and cosecant. Cotangent and cosecant are exactly like tangent and secant, but with negatives thrown in. So I'm going to focus on these ones, again, to keep the video from being a million times long. If the powers are all even, you're going to still use u substitution. You're going to use tangent x, and the reason for that is then your du is equal to secant squared, right? Remember we talked about even. Oh, look, that's even. So in this case, we have tangent to the 6th x. We want secant squared as our derivative. So then we have secant to the 4th becomes 2 secant squareds. So here's our du. Here's one of our u's, so that means that we need to rewrite this secant squared. And you're going to do that by using one of your other Pythagorean identities. Secant squared is equal to 1 plus tangent squared x and times secant squared x dx. So when you use this u substitution, you get u to the 6th times 1 plus u squared du. And again, you've turned it from a complicated trig integral down to a polynomial. And I'll let you again check your work with integrating that polynomial in the PDF. Last case is that if we're looking at sine, we're looking at secant, tangent, cosecant, cotangent, and we have odd powers, that means that your u is going to be secant, because then your du is equal to secant x tangent x dx, which are, as you see, odd powers. These are the least common types. You will run into one or two of them. What I would recommend that you do for this problem is go and look at the PDF to keep this video from being, again, a million times long, but you'll do the same idea. You'll say, okay, well, I want secant and tangent, so I want to have a tangent factored out, just like we would before. And since we also want a secant in there, I am going to factor a little bit farther to say I want tangent squared x, and then another tangent squared, which would is secant squared x minus 1, and tangent x dx, like so. Then what I would do is I would distribute and break it up into different terms, as you'll see in the examples, and you have your different steps to work through this very lovely integral. If you have questions, please first look at the PDF and then of course set up a Zoom call. If you're stuck on any homework questions, nominate them and leave them in the form. A lot of you have stopped doing that, and I think it's mostly just because you've forgotten that that's an option. So please avail yourself of that help as well. Talk to you later.